Okay, so good morning, everyone. Today I'll just continue in a pre-recorded lecture the discussion on plate tectonics. So last recording, we've discussed yung continental drift and seafloor spreading, which is basically the or baseline theory, kumbaga, that eventually led to the discussion on plate tectonics theory. So the plate tectonics theory suggests that basically the Earth's lithosphere can be divided into different plates, and these plates are moving on top of the asthenosphere, which is relatively plastic and can therefore flow. And yung lithosphere natin on top of the asthenosphere is capable of moving, um, and therefore there are areas where these plates are moving away from one another, or there are areas where the plates are colliding against each other, or just basically just moving past each other. So those are the three plate boundaries we've briefly discussed before. Okay, so as I also mentioned before, yung studies of Harry Hess revealed that new oceanic crust is basically formed along spreading centers, specifically along oceanic ridges, and they are consumed along subduction zones, specifically along trenches. Okay, so let's talk about additional evidence from the time of the continental drift theory and seafloor spreading to what we eventually have now, plate tectonics theory. So what were additional evidence that further proved that these plates or our lithosphere are actually or our lithosphere is actually moving. So first evidence was, of course, the paleomagnetism. Paleo means old in geology, so it's old magnetism or fossil magnetism. So the concept is that whenever we have as we will learn later on, rocks are basically the first stage, kumbaga, sa history of of a rock. A rock is actually its crystallization from from a magma. So from a molten material, it solidifies and transforms into a rock. Okay. In that process, some rocks contains an abundance of magnetic minerals, specifically magnetite, for example. So when this magnetite has a certain temperature, which we call Curie point, at which yung magnetism ng mineral na yon is lost. Okay? So anything more than 585, for example, as it is being crystallized from a magma, which is typically around 1000 degrees Celsius, they start to solidify and lose their magnetism as the temperature drops below their Curie point. Okay? So anong importance nun? Well, as in the meantime, while they are magnetic and surrounded by a molten material, they behave like a magnet floating on top of water. So basically, if you try it for yourself, get a glass of water, put a magnet there, you my north and south pole, and then if you put your magnet there, it will actually rotate. You can try this for yourself. It will rotate depending on the location of the geographic north, or the magnetic north rather, the magnetic north and the magnetic south. So of course, the south pole of your magnet will be attracted to the north pole, Earth's north pole, and the south pole of that magnet will be attracted to the Earth's. Sorry, balik that. So the north pole of that magnet will be attracted to the Earth's south pole, whereas the south pole of that magnet will be attracted to the Earth's north pole. So, yun yung effect niya. So, in in a similar way, magnetite in early forming rocks, or as they crystallize, they behave that way so that they point kung saan yung magnetic north or magnetic north and magnetic south during their formation. So when deep ocean lava flows occur, small magnetite minerals are crystallized and point towards the magnetic north during their quote unquote birth, or during their crystallization. Okay. And eventually, when these rocks gets moved, if, for example, if totoo yung plate tectonics, then yung oceanic lithosphere natin, as we said, they start moving because it's a lithosphere. And when they start moving, supposedly, yung location ng magnetic north na tinuturo ng old rock na yon no longer points to the geographic or no longer points to the present day magnetic north. Okay, at present, of course, our magnetic north is roughly close to the geographic north. So if you have an old crust, for example, hundreds of millions of years, uh, na nag-lock in, kumbaga, ng kanyang magnetic north, by the time na sa present na siya, posibleng hindi na niya pinopoint yung geographic north or yung magnetic north today kasi nag-move na yung block containing it, and the magnetism is basically locked in or fossil or solid na dun sa magnetite na yun. So that is what we refer to now as polar wandering, when you have series of rocks which apparently show the movement of the magnetic north, whereas we can actually think of it as, instead of the minerals pointing to different magnetic norths, it's actually the rock being moved so that it now points to different magnetic north. So for example, these are rocks, 500, 400, 300, 200, and 100 million year age, uh, from North America. Ito naman yung sa Eurasia. As you can see from here, at different times, or rocks crystallized at different times points to different magnetic norths. And even rocks formed at the same time, for example, that in North America versus that in Eurasia, points to distinct locations of magnetic north. So if we were to ignore yung plate tectonics theory, if we were not to subscribe by it, then that this just means that you have different magnetic norths, or your magnetic north moving from time to time. We call that polar wandering, and more on, and as a function of this observation, that there are multiple magnetic norths at any given time. We now know that that's not the case. Yes, the polar magnetic north or magnetic south actually moves a little, but a few kilometers, not thousands of kilometers as suggested by these diagrams here. So this apparent polar wandering path for North America and for Eurasia, we now know actually represent the movement of this North American plate and Eurasian plate through time. Okay, so either we have the magnetic north moving from Hawaii to North Pole, or the lava flows that contain the magnetic minerals are the ones that actually move. So which ones is true? We believe that this is the case. Lava flows that contain the magnetic minerals moved through time. Okay, and ang alam na, aside from that, we know that there are also magnetic reversals. For example, when we look at mid-oceanic ridges nga and the basalts that are being formed there, some volcanic rocks, in some volcanic rocks, the magnetic north is corresponding to the, or rather, the magnetic north corresponds to the geographic north. Yan. So we call that normal polarity, as is today. So today, di ba, yung magnetic north natin is located to our geographic north, roughly located to our geographic north. But there are also times during magnetic reversals wherein the geographic north is actually, or actually corresponds to the magnetic south. So yun naman yung tinatawag nating polarity reversal. So here we can see, for example, periods, itong mga red lines, for example, na yung ating magnetic north is located in the geographic south. And then there are periods na the geographic north corresponds to the magnetic north as well. So yun yung using a magnetometer, which as you can infer, this is a meter for the magnetic properties of the minerals in the rocks. We can actually picture, or we can imagine, or we can visualize rather, kung paano nagpapalit-palit itong magnetic poles ng Earth natin. Okay? And as you can see, itong parang barcode nito na to, they are mirror image of one another because, as you know, along mid-oceanic ridges, yung oceanic crust is formed in both directions. Both, kung ito yung spreading center, new oceanic crust is formed here and here, to the right and to the left. Okay? Another evidence that we learned is hotspot volcanism. I think briefly na-mention ko na siya before. Hotspots are basically areas of abnormally high geothermal gradients, meaning from the core to the crust, sobrang taas nung temperatures. This results to significant melting along that region, and when you have melting, you have volcanoes. So These volcanoes tend to form or sometimes form islands or hotspot island, or like volcanic islands, which are the product of these hotspots. Basically, the magmas coming from the depth of the earth rising to the surface. Yeah. So for let's look at, for example, yung um, Hawaii Seamount chain, which is connected. Uh, Dito. So we have here the Hawaiian Seamount chain and the Emperor Seamount chain. So what happens there is that you have this oceanic lithosphere on top of this relatively immobile, so relatively hindi siya gumagalaw na mantle plume. So when you have this plume and then you have this plate moving on top of it, every now and then ibang locations ng lithosphere yung nasa on top of the hotspot, and therefore the volcano that's actively or that has activity also changes through time. For example, at time 1, dito nagpa-punch yung heat, and therefore you have a volcano here. Eventually, when the lithosphere moves, it forms on a different location, and then this older volcano, itong volcano na nandito sa side na to, will eventually lose yung source ng magma, and eventually mag magsiseize, matatapos yung activity in this region. So in some areas, this is very prominent, such that the active volcano, since it's a relatively shallow area, marine organisms love that. So you have coral reefs fringing the island. And then, pag wala na yung lithosphere on top of the plume, it can the island starts to be eroded, essentially, eventually leaving behind a barrier reef, which is basically the same reef as before, pero this time yung volcano na kung saan sila tumubo is slowly eroding until eventually it's transformed into a guyot, so flat top seamount. And when it's a flat top seamount, meron ka pa ring carbonates or marine organisms, specifically coral reefs, growing on top of that. Then you eventually lose, kapag guyot na siya, di ba? So pag guyot, it's a seamount that's basically flat top kasi fully eroded na yung top of the mountain. So fully eroded na yung mountain, all you can see now is a ring of carbonates or of carbonate deposits, coral reefs, and we call this now an atoll. So in this way, volcanic islands are actually evolving as well. Yeah, so and their evolution is tightly linked to um, uh, plumes or hotspots like this one. So ganun yung story nitong si Hawaiian chain at saka si Emperor Seamount chain. And what's interesting here is that actually, so of course the present day activity is in Hawaii. That's why you have a lot of volcanoes here, active volcanoes. If you look at the islands that are to the west of Hawaii Island, we see that their volcanic activity gets older and older, giving, yeah, as explained before, suggesting yung movement of the lithosphere on top of this plume, moving this way, so that ito yung dating at 3.8 to 5.6 million years, this was actually the active volcano, and then this one during 2.2 to 3.3, Molokai during 1.3 to 1.8, and then Maui less than 1 m. And then nag-move na naman siya, so that 0.7 million years, so that 700,000 years to present, yung activity is constrained only in Hawaii. As soon as this plate moves again, so pag nag-move ulit yung oceanic lithosphere sa taas na to, which is the Pacific Ocean actually. So when the Pacific plate moves, there will be a new volcanic center towards the northeast of this Hawaii island. Yun yung story nitong Hawaiian seamount chain. As you can see from here, yung Hawaiian seamount chain has a different trend or has a different trajectory compared to the Emperor Seamount chain. And this actually represents the period na nagbago yung motion ng Pacific Plate. So, hindi lang, so sabi natin yung Pacific Plate is moving this way, that's why yung hotspot goes always towards the northeast. But then, sometime 65 billion years ago, nagbago actually yung motion, so that you have two different trends from an Emperor Seamount chain to Hawaiian Seamount chain. First, you can think of it as, ano ba, ganyan muna, tapos nag-rotate yung Pacific Plate, tapos nag-move siya ulit pa ganon, so that you, di ba, change ng plate motion na yon, resulted to this two chains of volcanoes. Yeah, so we have two additional evidence, paleomagnetism and Hawaiian seamount chain, together with the paleontological evidence, first used during the presentation of continental drift, as well as yung new oceanic crust nga during the uh, data when seafloor spreading what was put forward. So itong evidence na to was basically all the evidence that we now use to prove plate tectonics theory, or as evidence for plate tectonics theory. So the question now is, when you if you have these plates, um, basically, if you have the lithosphere being nito, distributed or being uh, divided into plates, nasan yung divisions nila? Nasan yung boundaries of these plates? And uh, we now use yung seismic activity or the location of earthquakes to define kung saan yung plate boundaries natin. So each dot here represents one earthquake event. And as you can see, the earthquake throughout the world is actually not randomly oriented. Although it may feel that lahat ng or buong mundo experiences earthquakes because of the news, it's actually located in only a very few areas, okay, of the world. For example, as you can see, much of the earthquakes are basically located in or most of the earthquakes are actually useful in since they are located along plate boundaries. Okay, so again, here in mid-Atlantic ridge, which is a spreading center. So these are areas where new oceanic crust is formed because the plates are moving away from one another. You get a lot of volcanoes in areas like this in South America, North America, in the Philippines, Japan, and here in New Zealand, Papua New Guinea, we also see a lot of earthquakes. And when we look at the depth of the earthquake, they actually vary. They actually vary. So you have shallow earthquake, 0 to 33 kilometers, marked by these red dots. The yellow ones are 33 to 100, whereas eventually you reach the blue ones which are 400 to 700 kilometers. So basically, from this side, from the east side towards the west side, you get deeper and deeper earthquakes. As I mentioned before, this progressive increasing in depth of the earthquakes is actually a function of the subduction. So uh, if we look at spreading centers or oceanic ridges, these are areas where new oceanic crust is formed. Dito naman sa trenches, these are areas where the oceanic crust is basically subducted or basically forced downwards and being consumed. And as they are consumed, they generate earthquakes. Okay, so these subduction zones, and you can go to Google Earth, for example, to see kung ano yung physical manifestation of this subduction zones. These are actually where we find trenches. Yan. So areas of spreading, we have earthquakes. And of course, it's shallow earthquakes because it's just in the surface, okay, as the new plates move around. And then also, we've discussed before, when you have moving or plates moving away from one another, you also generate transform faults or faults in along which the plates just glide past each other. So hindi sila nag-spread, hindi sila nagko-collide, but they just move past one another. So those are the transform faults that we can see here. So for example, this is a spreading center, this is a spreading center, this is a spreading center, and it's translated. It's basically displaced by this large transform fault. So yun, those are the three plate boundaries, and we can clearly identify them based on their seismic activity. Of course, there are areas na out of nowhere biglang may volcanoes like this in Hawaii. This is actually the area of Hawaii, and ito naman ay related to the volcanic activity, as you can imagine. So if you have magma rising to the surface, the magma or the molten material basically pushes against the surrounding rocks, and as it pushes against the surrounding rocks, it generates earthquakes. Meron ding mga man-made earthquakes, and that's very obvious here in USA. You can see here in central United States, wherein wala namang trenches, wala namang new oceanic crust being made, you still get these earthquakes, and some of these at least are attributed to fracking, yung ano ito? Industrial method for extracting new oil by basically breaking the rocks under our feet, beneath the feet, thousand or kilometers below the feet, below our feet, to basically increase yung permeability or basically yung capacity for the fluids to or for the natural gas and petroleum products to easily rise to the surface. We see that here. Dito, we also see rifting in continents. So this uh, red dots here, this line of red dots here, are actually corresponding to the spreading along the African plate. Yeah, eventually a new oceanic crust may be formed here, but that would of course take at least few million years, tens of millions of years. Okay, so the seismic activity defines yung ating plate boundaries. The deep earthquakes are corresponding to the trenches, and the location of the shallow earthquakes demarcates yung boundary ng ating different plates. Sa subduction zones, yung deep earthquakes shows the location of the subducted slab, so yung pumailalim na slab, whereas shallow earthquakes are areas where the plates are rifting away from one another and therefore causing shallow earthquakes. So, the plate tectonics theory again suggests that the lithosphere is a rigid layer. It's broken into segments, which we refer to as plates. And these plates drift independently. As, di ba? Ito naman yung original idea ni Alfred Wegener when he proposed continental drift theory. So the question then, and the question which we will answer now, is why or how do they move? We now know that it's not because of the tides or it's not because of the gravitational pull of the moon as Wegener first proposed, but rather it's due rather to convection along the or in the mantle. When you have temperature difference between the core towards the crust and the crust, then inevitably you generate convection cells to transfer the heat from the warmer core towards the cooler crust. So does this mean na after billions of years, eventually, pag na-transfer na lahat ng heat from the core towards the surface, wala ng plate tectonics? Yes, possible, but this will take a very long time. Yeah. So let's now talk about the different plates or the plate boundaries. So there are 6 major plates: North American plate, South American plate, Pacific, Eurasian, Indo-Australian, sometimes Australian Indian, and then Antarctic plate. Take note that these are plates. Okay. The reason why Pacific here is with an asterisk is that it's the only plate which is comprised of a single type of which is comprised of a single type of crust. So only Pacific is composed of oceanic only type of crust. North America, South America, Eurasian plate, all these other plates are continental and oceanic crust. So itong mga plates na to ay hybrid kumbaga. Okay? So for example, you can just imagine Indian and Australian plates being separated by the Indian Ocean. Yeah, so here you have the obvious. But anyway, you have here India and you have here Australia. Separating those two is actually the Indian Ocean. So, but even though they are composed of continent, oceanic crust, they are moving the same direction, they have the same boundaries, and therefore they define a single plate. Okay. Yeah. And then you have minor plates. So these are plates that are also relatively large, but not as big, not as large as these major plates. So these plates move with respect to one another without the Earth expanding, because in some areas the two plates move away from one another, creating new oceanic crust, and we call these divergent plate boundaries. In areas where they collide, where two plates collide, these are areas of convergence, so we call them convergent plate boundaries. This results to, since you have two types of crust, oceanic, continental, when there's an oceanic crust involved, it results to arcs. So oceanic or oceanic continental collision, this results to the formation of chains of volcanoes, which we refer to as arcs. Okay? Paano naman pag continental? Continental, you form what we call orogenic zones. So orogenic zones are basically zones of continent-continent collision, and what you have is mountain building, wala kang subduction because continental crust is more less dense rather. Continental crust is less dense than oceanic crust, and when you have two, when you collide oceanic continental, since meron kang denser material, the oceanic, it immediately or it proceeds to subduct. It proceeds to go beneath the continental crust. But when you have two relatively buoyant materials, continental, wala talagang subduction na mangyayari. Collision lang yung mangyayari. And then, as I discussed before also well, where two plates grind past each other, we call that transform plate boundaries. So this is how they look like. Here you have oceanic plate, the Nazca plate, subducting beneath the South American plate. So that's an oceanic against continental collision. So you form this chain of volcanoes. We'll discuss later on yung melting process na yun. But yeah, you form this chain of volcanoes. At the same time, when you have spreading centers like this, or even collision zones like this, you have transform faults, or we encounter this transform faults which connects yung ating plate boundaries. So along transform faults, new oceanic crust, no new oceanic crust is formed nor destroyed. The plates just move past one another. And then you also have, of course, divergent plate boundaries, which are areas where new oceanic crust is formed and where the crust is basically moving away from one another. So let's discuss that in more detail. The divergent plate boundaries are characterized by spreading centers. These spreading centers may be formed in continental areas or continental crusts. We call that continental rifts. Or pwede rin siyang mag-progress further into new oceanic ridges. In both areas, these are areas where new oceanic crust is formed by separation of the old. The width of such spreading centers range from 1,000 to 4,000 kilometers. And take note the rate of separation, 2 to 15 centimeters per year, with an average of 5 centimeters per year. So in a decade, or in a century pala, in a century, it will take a century, for example, for a movement of around 2 meters. Is it 200 centimeters? So 2 meters, diba? So uh, one century, that's two generations already. So it will take two generations just for a movement that is equivalent to the height of man, for example, of a typical man. Hindi nga, matangkad na nga, sobrang matangkad na nga yung 2 meters eh. So, average, for example, 100, sa Pilipinas, 150 centimeters. So, even if we take this average, di ba, it will take more than decades bago ma-reach yung height ng isang tao. So this process is really, really slow. And therefore, that's the primary reason why the idea of continental drift theory was first ridiculed and was not understood easily. Okay? So, sabi natin kanina, yung oceanic ridges are areas where oceanic crust is formed, and although they are denser, we discussed this in planet Earth, oceanic crusts are actually thinner but denser. So their maximum thickness is only the whole lithosphere na to, meaning kasama na yung upper mantle. The maximum thickness of oceanic lithosphere is only 100 kilometers. Manipis yan. For example, a continental crust lang, so crust lang, ang average thickness nila ay 70 kilometers. So that's crust plus mantle, sobrang kapal ng continental lithosphere compared to oceanic lithosphere. And it takes a long time for it to be this thick. So it takes 80 million years. Okay, so this is an example of a spreading center. This is the Mid-Atlantic Ridge, the spreading center which separated North America from Europe, South America from Africa. But of course, it must have started like so. So it must have started as continental crust that was spreading, and this spreading may be due to, kunwari, you can think of the, ano kanina, yung hotspot. Some say it's the hotspot, which led to the weakening of the overlying continental crust, eventually leading to rifting like this, continental rift, until eventually it formed linear sea until eventually an ocean. Others contend that it's the other way around. The movement of the continental crust actually causes upwelling, much the same way na kapag if you have a water, kunwari sa timba, in a giant uh, lalagyan, for example. If you move your hand across the topmost portion of the water, then it will cause the upwelling of material from sa ilalim. So, baka daw ganun naman siya. It's the reverse. Either way, uh, in any kung ano man yung nauna, yung plume or yung action ng rifting, in both cases, the result is the same. You have oceans being formed eventually from what was or what is originally continental rift. So, okay. And then areas naman of subduction or areas of convergence. Okay, so convergent plate boundaries naman where areas or where plates, areas where plates collide. Okay, so again, you have two types of crust. You have oceanic and continental, and therefore you have oceanic, oceanic continental, or continental continental. So for the part where you have oceanic, you have basically density difference between the oceanic crust, which although younger in general and thinner than continental crust, is actually denser, and this density difference causes the oceanic crust to start going beneath the other plate, the other continental crust, which leads to uh, arc arcs. So continental volcanic arcs. Paano naman kapag oceanic? So ganun din, when you have oceanic, generally the denser oceanic crust, the older oceanic crust is generally denser than younger oceanic crust. And this means now when two oceanic crust collides, the older plate actually goes down. Okay, so siya yung nagsasabrak. And the volcanic island arc, is formed on the younger oceanic crust. So density or age difference causes subduction, which then causes partial melting, forming either volcanic island arcs when you have oceanic, or continental volcanic arcs when you have oceanic continental. When you have a subduction zone rather, you have a subducting slab or the downgoing slab, the overriding slab or the one that is on top, and the mantle wedge beneath them, between them rather. So here you have you have here the subducting slab, the overriding plate, and of course the mantle wedge beneath them or between them rather. So ito yung volcanic island arc, and then you have island arc kasi usually this forms chains of islands. Okay? Volcanic islands. For example, sa Pilipinas, you can think of this as the Batanes group of islands plus the Babuyan group of islands, which is the northernmost boundary ng Pilipinas. So this group of islands are actually volcanic island arcs. Ganon din yung continental volcanic arcs naman, on the other hand, are those that are formed on top of continents. Yeah. So for example, sa South America, itong chain of volcanoes na to sa Chile. Ayan. And yung sinasabi ko kanina, yung subducting slab natin, we've been able to image that as the uh, Wadati-Benioff zone. So ito yun siya. So the Wadati-Benioff zone, this one, basically demarcates or basically is the location of the different of the different earthquakes generated by the subducting slab. So here in Japan, for example, so we know that there is the Pacific plate here subducting beneath the Japan island. That's why they also have a lot of volcanoes. Fujisan rather, Fujisan for example, and that's because of this subduction. Ganun din yung sa Chile. Yeah. So this represents the slab. So you can see from here that the slab ranges from 100 kilometers all the way to 400 kilometers. Yeah. What about when you have continent? So by the way, please remember the term Wadati Benioff zone, ha? Okay. Paano naman kapag continent? Well, when you have continent, there is no subduction because of course there was subduction before at one point, since usually oceanic crust ahead of that is a continental crust. Usually ahead of that is an oceanic crust. So when the oceanic crust interacts with the continental crust, of course it starts to subduct and form continental volcanic arc. But eventually, the oceanic crust between them gets consumed, and eventually it will be continent versus continent. So that is what we refer to as orogenic belts. So when you have continent, you have a downgoing plate, but it's not really subducting. So it's buoyant, so it cannot subduct, and because of that, it only forms the high mountain ranges that we know existing today in Himalayas, for example, north of India. So the story of India, as you can see from here, originally it was located much south. It was actually attached to Antarctica, the present day Antarctica. So you can just imagine kung gaano siya ka-south. It was located south, southern hemisphere, and then rapidly drifted towards the north. As it drifted, it has this oceanic plate on top of it, ahead of it rather, on the north of it. And as it moved northwards, itong plate na yon, na to, oceanic plate na to, got consumed and resulted to volcanic islands and island arcs as well. And eventually, once the oceanic plate was consumed, you have this orogenic belt. Right? Throughout the world, you'll see a lot of orogenic belts. For example, in Europe, the mountain ranges, the Pyrenees, the Alpines, these mountain ranges, which separates the different countries of Europe, these are actually orogenic belts. Different times, but still the same concept. Ayan. And then transform plate boundaries, they are basically ridge systems, or rather fault systems, which connects the different plate boundaries. So they divide the Earth's lithosphere into rigid plates. So here you have two or three spreading centers, and then they are interconnected by transform faults. Okay. So, what drives plate motions? Sabi natin, so as far as we know, a stenosphere is hot and relatively weak, and therefore capable of exhibiting fluid-like convective flow. And therefore, since it's capable of driving convective flow, there must be a reason kung bakit siya nagpo-flow in the first place. And we think that's because of the transfer of heat, basically, from the hot core towards the cool crust. So the thermal difference basically drives this mantle convection. There are also some general agreements. So again, convective flow is the underlying force. Mantle convection and plate tectonics are part of the same system, and that convective flow in the mantle is the prime mechanism for transporting heat from the core towards the space. So there are also, of course, remaining questions such as how does this mantle convection work? Is it a two-cell convection so that you have a convection in the mesosphere, convection is in the asthenosphere, or is it a single convection cell like this one? And what are basically the effects of other components of the system, such as hotspot volcanism, paano siya form in the first place? Some argue that hotspots are only from the um, mesosphere asthenosphere boundary, but others argue it's all the way down to the outer core mesosphere boundary. So which is which? Diba? What about the motions of this slab? Maybe this subducting slab is already too dense so that it's not actually convection here, but it's actually this one being, or this plate behind this one being pulled by this subducting slab. Baka naman itong mid-oceanic ridge, these are not actually areas kung saan nagsa-separate yung plates because of cells, but rather it's the other way around. Baka naman yung mid-oceanic ridge or yung movement or yung moving away of the two plates along mid-oceanic ridge that actually drives uh, yung convection. So there are still competing ideas. Ayan. For example, what are the effects of slab pull and slab push? if by themselves can they generate yung convection cells. What about the mantle drag between the plates? Itong separation between the lithosphere and the asthenosphere. So these are questions that are basically finer details ng plate tectonics, but the general idea is there that you have plate tectonics because you have the lithosphere being divided into plates. They are moving around because of the convection heat transfer from the core towards the crust. And plate tectonics is very active. So for example, this represents the current or the present day movement of the different plates. And as you can see, Antarctica is relatively not moving, so it's relatively static. South America and North America are also relatively static. The Mid-Atlantic ridge has long ceased to spread, so wala na siyang active spreading in most areas, and therefore, wala nang movement yung North America and South America. So these are relatively immobile rather. The much of the activity is coming from these plates in Eurasia, Africa, and Australia. And eventually, based on our current, if hindi magbabago yung GPS or yung movement direction nitong mga plates nito, which we now know by using GPS, ganito daw yung magiging itsura ng next supercontinent. So as you can see from here, the next supercontinent, if everything doesn't move, doesn't change their movement directions, will basically see the Philippines, Indonesia, the rest of Asia basically colliding with the rest of China, Mongolia, etc. Ayan, forming the next supercontinent. Antarctica, which is relatively immobile, will be left out of the picture. And again, this is just a model showing 50 million years from now, but we don't really know if magbabago pa bigla yung plate motions nito, which is certainly possible as we've seen sa Emperor Seamount Chain vis-a-vis Hawaiian Seamount Chain. Yeah. And then this brings us to the last part of the lecture, which is Philippine tectonics. So, ano naman yung plate tectonics sa Pilipinas? This is a map of the Philippines created by plotting all the earthquake epicenters for the last 100 years. So 100 years of earthquakes in the Philippines island. As you can see, the whole Philippines is literally dotted with earthquakes bukod sa Palawan, so that you can see almost every island here, diba? And we can see that again here. Hindi lang siya earthquakes like this. Again, parang yung map before. This map shows the different epicenters of earthquakes at different depths. And this, of course, are linked with volcanoes. So you can see here, you have arcs being formed because of subduction zones in either directions. In the west, you have the Manila Trench, the Philippine Trench. In the west muna. So yeah. So you have these volcanoes because of the subduction, and you have earthquakes also because of the subduction. So what does this mean? What this means is that the Philippines is basically uh, located in a region of convergence. So we have 23, actually 24 active volcanoes. We are actually part of the Pacific Ring of Fire, which again, despite the name, does not is not part of the Pacific Plate. So the Pacific Ring of Fire is just the term, non-scientific term, non-technical term for the ring of volcanoes lining yung Pacific Ocean supposedly. But as we learned, the body of ocean or the body of water to the east of the Philippines is actually Philippine Sea Plate. So there is a distinct boundary, tectonic boundary, plate boundary between the Philippine Sea Plate and the Pacific Plate towards its west. Okay, so I hope that's clear. Philippine Mobile Belt, Philippine Sea Plate, and then Pacific Plate. So, although tinatawag tayong part of the Pacific Ring of Fire, actually, hindi tayo technically nasa Pacific. Okay? So, non-technical term nga. So, and also, there are earthquakes all throughout the Philippines besides Palawan because we are basically a convergent plate boundary. So, here you have oceanic, um, resulting to mature island arcs. So you have basically the Philippine Mobile Belt being formed. So the rest, this Philippine Mobile Belt actually basically one oceanic crust um, that was, or hindi naman single, pero multiple oceanic crust that was basically parang joined together because of these collisions, because of this convergence, and because of this arc magmatism. So as you can see from here, basically volcanoes line up the Philippines since hundreds of millions of years ago. Okay, yan. And then, so much of the Philippine Mobile Belt is oceanic in nature, but there is also a continental crust dito sa ating region. So actually si Palawan and we think itong si Zamboanga Peninsula, these are regions of continental material. So continental material to sila now colliding against the rest of the oceanic Philippine Mobile Belt. Yan. Okay, so you have continental versus oceanic. So in the Palawan microcontinental block being continental against the mature island arc, the Philippine Mobile Belt. So let's discuss in more detail yung tectonics ng Philippines. You have this one. You need to memorize this part. So basically, the Philippines is the kumbaga interaction or sees the interaction of three distinct plates or two distinct plates pala. You have here the Eurasian plate. Yan. All of this is the Eurasian plate. Lahat ng nasa west natin ay part ng Eurasian plate. So South China Sea, Palawan Mindoro Continental Block, Borneo to the southwest, and then Celebes Sea, Sulu Sea, lahat yan ay Eurasian plate. And then to the east, you have the Philippine Sea plate. So you have an oceanic and you have here oceanic plus continental colliding against each other. These collisions led to subduction. So the Philippine Sea Plate is subducting beneath this island arc, and this subduction is along the East Luzon Trough and the Philippine Trench further south. So you have to remember that to the east we have the East Luzon Trough and Philippine Trench. To the west, you have oceanic material, oceanic crust ng Eurasian plate being subducted beneath this island arc as well. So para siyang double subduction. Hindi pala parang, it's double subduction. So in the west naman, we have the Manila Trench. Manila Trench is along which the South China Sea subducts beneath the Philippine Mobile Belt. Here we have the Sulu Sea subducting beneath the Philippine Mobile Belt along Negros and Sulu trenches. And then finally, the Celebes Sea crust subducts beneath the Philippine Mobile Belt along the Cotabato Trench. So you have to remember all these elements. And because of these collisions, basically, you also have these fault zones lining the country, and the longest of which, the most prominent of which rather, is the Philippine fault zone. So the Philippine fault zone runs from northern Luzon all the way to Mindanao. So this fault, which is a left lateral fault, as we'll discuss later on, this left lateral fault is the consequence of the basically plates being uh, squeezing yung Philippine Mobile Belt between them. So squeeze, you form deformation. So nasa-stress siya, and therefore it starts to deform and along this Philippine fault zone. So again, review: Philippine Mobile Belt, Eurasian Plate, Philippine Sea Plate. Philippine Sea Plate subducts beneath the Philippine Mobile Belt along East Luzon Trough and Philippine Trench. To the west, you have the South China Sea, Sulu Sea, and Celebes Sea, all part of the Eurasian Plate. So South China Sea subducts beneath PMB, Philippine Mobile Belt, along Manila Trench. Sulu Sea subducts beneath this Philippine Mobile Belt along Negros and Sulu trenches. And then Celebes Sea subducts along Cotabato Trench. Please remember all these elements. Okay? Memorize these elements. Okay. So just a quick cartoon kung bakit daw na-extinct yung dinosaur. Maybe Noah did not let them ride the ship. This is from an old newspaper. Okay. So that's it for today. And we'll have a quiz. So I'll try to meet you on Thursday, but if not, because of the time difference, I may not be able to meet you this week entirely. If ever, anyway, I will meet you on Tuesday next week. Okay? And doon na lang tayo mag-quiz on plate tectonics. Okay? So this will be a slightly longer quiz, maybe 15 item quiz on Tuesday. Okay. Thank you guys. See you.